So our next speaker, our first speaker, first keynote is dear Olga Sorkine-Hornung, who is a professor of computer science in ETH Zurich. And her title is 20 Years of Mesh Editing, What We Learned and What to Learn. She is a professor of computer science at ETH, where she leads the Interactive Geometry Lab, IGL, all the libraries that you use. Yes, the IGL comes from there, right? And then prior to joining ETH, she was an assistant professor at the Courant Institute of Mathematical Sciences in NYU. She earned her bachelor's in mathematics and computer science and PhD in computer science from Tel Aviv University. And following her studies, she received the Alexander von Humboldt Foundation Fellowship and spent 2 years as a postdoc at the Technical University of Berlin. Her interests are computer graphics, geometry processing, shape representation and modeling, and discrete differential geometry, all of which we are very much a fan of course, because why else are we here, right? And she published over 140 peer-reviewed articles in top venues. We know her papers. She served as a member of the ACM Turing Award Committee, including serving as the ACM Turing Award Committee chair for 2020. Whenever the microphone is going off, I am yelling. I hope it doesn't come back when I'm yelling. She received several scientific prizes and awards, including the ERC Starting and Consolidator grants and the ACM SIGGRAPH Significant New Researcher Award at the Eurographics Outstanding Technical Contributions Award. She's such an impressive biography. I want to read it all. Sorry about that. She's a fellow of the ACM and the Eurographics Association and a member of the Swiss Academy of Engineering Sciences. We have such a brilliant keynote to start with. Thanks for being with us, and the stage is yours.
Thank you so much, Ilke, for this incredibly kind introduction. I am so excited to be here. I'm also very anxious because the title of the workshop is Deep Learning for Geometric Computing. And I'm afraid that 95% of my career was spent on classical geometry processing and geometric modeling. And the talk will be the same, as you will see. So I cheated a little bit. I hope that, I won't get evicted from CVPR. It's also my first time at a computer vision conference and at CVPR in particular. It's very overwhelming and very exciting to be here. But so I'm hoping that this is a safe space where, non-deep learning methods and interactive methods are also accepted. So, as you know, my research is on shape modeling and geometry processing, and my interest in this area started over 20 years ago, in particular inspired by the fact that most physical objects that we see around us are actually first designed and maybe tested and simulated on computers and only then physically manufactured. But then, of course, also digital 3D content is in high demand, and these days even more so with the advancements in VR, XR, mixed reality, and so on. So just yesterday, I attended the mixed reality workshop here. That was very popular, seemingly, and a lot of geometry and even SIGGRAPH papers were talked about there. So it was very exciting to see. So in our research, mostly we're focusing on the mesh shape representation because it's a very powerful and flexible shape representation. You can represent any topology, you can go to arbitrary resolution and have a lot of surface detail. And also acquiring such representations from the physical world is quite well understood, right? Scanning and then surface reconstruction. But meshes, as you all probably know, are not the most simple representation for doing something with the shape later, such as editing it, animating it, and so on. Because meshes don't have a built-in mechanisms for deformations and other modifications. So here's where algorithms come in. And in particular, I mentioned already I work on interactive shape modeling, and it's in the name of the lab, even Interactive Geometry Lab. So basically there is some user in the loop. The user is, for the most part of my career, was a human, but now increasingly users can also be AIs or algorithms, as I call them. But in any case, there are some, it requires some way of controlling what's happening with the shape, some handles to manipulate, or some way of accessing the shape and its modification modes. And in an interactive setting, tools need to be intuitive or explainable, maybe we would say today, somehow. So whatever the algorithm is doing should be clear to the user so that manipulations have an intuitive and predictable effect. So there are a lot of trade-offs in this space, accuracy versus speed of the algorithm. If something needs to be interactive, obviously it has to run very fast. Otherwise, creativity and interaction don't happen very well. And there's also this notion of freedom, so freedom to be able to do whatever is your idea about the shape, and also control. Right, so in this general space, a lot of my research over the years has focused on shape modeling via the means of deformation. And in particular, since we're talking about meshes, as mentioned, there are no built-in deformation handles or modification handles. So this happens typically using a variational approach, right? We have our starting shape S, and then we're designing some kind of deformation, which is basically a modification of the shape, finding new coordinates for the mesh vertices. And this modification happens via optimization of some kind of energy function or loss function that basically measures the quality of that deformation. So very generally, we call it E. And it can be an integral. Typically, it's an integral of some local properties on the shape that we are measuring. And we also have these controls that we express as constraints. So in the most simple way, simple form, it's a positional constraint. So basically some points or regions on our shape, we're fixing their location to be stationary or to be a certain prescribed location by the user, such as these points here, the purple areas and points on the animation you see below. So these are our constraints, and we're trying to minimize some function based on taking care of those constraints. And in the discrete world, again, on meshes, nothing is really differentiable. So we have to replace everything with a discrete form. So the energy becomes some kind of summation over quantities that are defined in terms of the mesh vertex positions xi typically. And so I want to give a sort of historical, very biased, but historical retrospective of how people have been thinking about this problem, and in particular in my own research. And I would say that in the early 2000s, that's when it really boomed and started this, this type of research on variational deformations. People really focused on the question of what is a good deformation energy. So how to define this E functional. And all kinds of wish list items have emerged, and in particular, it's generally accepted that the deformation energy should create a smooth deformation effect on the large scale and an as rigid as possible effect on the local scale. So if our mesh represents nice geometric details, we want to preserve those details as we manipulate the shape. And another very important point is the efficiency of the algorithm. So this E should be something efficient to minimize, because remember, we're in an interactive framework typically where we want things to happen in real time, or at least at a reasonable interactive frame rate. So I would say that the most kind of fundamental formula for E and all the subsequent formulas, they stem from this shell energy that was introduced by Tzopoulos and colleagues in 87. So it's pretty old, probably before some of you were born. But nevertheless, it's a very, I would say, yeah, it's the source of everything that came later. So it's very nice to look at it even today. So basically, it's a formula that describes elasticity, and it measures it in the most elaborate, precise way, I would say. So we have here basically a measure of the difference between the first fundamental form of the deformed object, this is this I prime, and the initial state I, and the same thing for the second fundamental form. So the first fundamental form is the metric of the shape. It measures how much things stretch, basically, or deform in the tangential space. And the second fundamental form is the bending of the shape of the surface. Bending and stretching are separated in this formulation, and it's kind of our gold standard for elastic deformations even today. The problem is that this is an extremely, we say, highly nonlinear energy. It's very difficult to optimize it. It would be super slow to do it in real time. So in practice, it's not really used outside of simulation and theoretical analysis of deformations. So basically, in the early 2000s, people focused on how to simplify and make this energy tractable, and a special focus has been given to bending energies, because that's kind of the main part of elastic deformation. So people in particular, very early, Humboldt and colleagues proposed to replace the second fundamental form with a Laplace operator. Right, Laplacian is the sum of second derivatives. So it's kind of logical that this could work nicely, and the Laplacian is something that's much easier to discretize and handle in general. In the discrete world, just as a small reminder, Laplacian is for a mesh one ring, it's the difference between the center of mass of the one ring and the center vertex, right? So it's this tiny little green vector over here that you see. So it kind of measures local surface detail, you could say. If the surface is flat, then the Laplacian is 0. And if the curvature is low, then the length of this tiny green vector is tiny. So it's a good stand-in for this elastic bending energy in the second fundamental form in particular. So one very simple proposal to replace, basically, if we're replacing second fundamental form with the Laplacian, what we can do is propose this very simple Laplacian energy as our deformation energy, right? We just measure the difference between the Laplacians, these tiny green vectors of our current mesh, and the original Laplacians that we call delta 0 here. Right, so here is the formulation in a little bit bigger font. And in the discrete case, we have very simple discretizations of the Laplace operator on meshes, the famous cotangent formula, for example. And this AI here, by the way, is the local area on the mesh, so like the Voronoi area of the one ring, for example. So it's, you can think of it just as a weighting term, or even ignore it, as many people did. So this energy was proposed the first time by Mark Alexa in his 2001 paper, and expanded on by many other researchers, such as Mario Bochlav, Humboldt, myself, and our collaborators. It's a very interesting energy. So it's, first of all, I should say that this is a quadratic expression. So minimizing it is just solving a sparse linear system. It's extremely efficient. So this could happen in real time, even 15, 20 years ago, which was quite impressive for that time. But it's not without problems. So if we look at this simple kind of didactic example, this is a bumpy plane surface. We are fixing the left side of the mesh, and we are taking this right-hand side boundary and pulling it upwards. Our intuitive expectation, if it's a kind of elastic surface, would be something like this, right? But what happens with this Laplacian energy is that it produces this result here. And the reason for that is that the energy measures the difference between the original Laplacian vectors that were for these bumps, they were somehow pointing upwards, and the current ones, and it's trying to minimize it, right? So basically, it's trying to preserve the original orientation of these bumps. So that's why they stay upwards. So it's not very nice, right? It's not the intuitive outcome. And so the main key question that people have been struggling at the time with was how to produce these local rotations. So essentially, we need to somehow rotate these little Laplace vectors and produce these RIs, the local rotation matrices. But we don't really know how, because it's a chicken and egg problem, right? We don't know the deformed surface. So how do we know what are the local rotations supposed to be, right? But somehow we need to figure them out. And a problem is that, yeah, of course, these rotations are functions of the unknown surface. And in any kind of reasonable constellation, they're a nonlinear function. So that kind of would break this whole desire of making this a quadratic energy and minimizing it efficiently. Nevertheless, you can do something. It's not completely hopeless. And in 2004, in the beginning of my PhD, that's what I tried to do. Basically, I said, okay, we can't take full-blown rotations, but we can linearize them. So we can take the first Taylor expansion, first order Taylor expansion of rotation matrices. It's basically an identity matrix plus skew symmetric matrix. So you see the form here. And you see here the relationship, kind of the conditions on the entries of the matrix are linear conditions, right? The diagonal should be all ones, and the off-diagonal entries should have this relationship that one is minus the other. And so overall, if we plug in this expression into the energy, it stays a linear, a quadratic expression. So it's a linear minimization overall. So what you see in this little video is historical footage from that original Laplacian mesh editing paper in 2004. So, I mean, it's kind of humbling to think that's been 20 years ago. And it looks a little bit, not very impressive now, but back then it was really something very special on those computers to see this kind of real-time deformation on real and actual detailed high resolution meshes. So this was kind of a big deal back then to be able to do that. Of course, we pay for this linearization, right? We win this real-time performance, but we pay for the fact that Taylor expansion only works in a small radius around the initial point, right, around 0 in this case. So for larger angle rotations, this approximation is not very good. It breaks. And so for this, again, for this bumpy plane example, you see that the deformation is sort of okay, but it's not perfect. And that's due indeed to that fact that it's only a good formulation for small rotations, and for larger ones, a lot of bending, it doesn't behave super accurately. So this was 2004, and a few years later, we became more brave, I would say, in the community. People got used to the fact that, yes, you can solve large sparse linear systems, and it's something that's doable. So why not solve them many times and iterate? And that's basically the basis of a nonlinear optimization algorithm, right? It's broken down into many linear optimizations, essentially. So in 2007, Mark Alexa and I worked on another surface deformation formulation that's called ARAP, as rigid as possible energy, where we said, okay, we will leave this local rotation to be nonlinear. So the idea is not to do any linearizations, but to look at the initial configuration of every one ring or every cell, local cell on a mesh, and to compare it with its unknown deformed configuration, and to define this this rotation R as the best fitting local rotation that would explain the deformation that happened here on the local scale. So of course, R is now a nonlinear function of the deformed positions. But the nice thing is that we have a good formulation for it. It's the so-called Procrustes problem. It essentially boils down to doing a 3x3 SVD if you know the positions of the initial one ring and the target one ring. So you just solve this best fit rotation. And they all can be solved independently of each other. So yes, the energy is nonlinear. It's actually very funky with this mean formulation, but in fact, it's not very, yeah, when you break it down, it actually has a very efficient optimization scheme. And it works like this. It's basically just a simple local global procedure where we start with treating the deformed positions X and these local rotations as separate sets of variables. And for fixed rotations, we just have a sparse quadratic energy here, so a sparse linear minimization that we have to do. And this L here is, by the way, it's just a Laplacian matrix. And then in the second step, we fix those positions that we solved for in the first step, and we optimize the rotations. And that's just optimizing all those little 3x3 SVDs in parallel for each one ring or for each cell that you defined on your mesh. And that's it. And you can repeat this multiple times iteratively. And the nice thing is that each step decreases the energy, or at least it's guaranteed not to increase it. So, so it's a very, very simple algorithm despite nonlinear formulation. And I think that's maybe the reason why it became quite popular over the years. So here again, some historical footage. In the beginning, it only worked on very low resolution meshes, as you can see here. So with this, it's hard to impress anybody today, and I won't attempt to do it. But the nice thing back then was that really it could produce these very large bends, you know, large rotation angles in real time, albeit on these, yeah, very, very coarse shapes. But it was, again, kind of a cool surprise to see that, that this formulation indeed works, at least in theory. The challenge is, of course, how to scale it onto real models that are not these toy examples. And this took some time, admittedly, and much better brains than mine. So basically, this was the topic of a PhD thesis of Alec Jacobson, my first PhD student, and he really did the proper job on this problem. So here was Alec's idea. Basically, you want to do optimization on meshes of higher resolution than this one, but it should be in a smart subspace. So today we would immediately jump to the conclusion that we should learn the subspace, and indeed people are trying to do that. But back then, again, we didn't have this deep learning technology. So we were thinking more in algebraic terms, right? So we have this energy minimization here, and X is very high dimensional. It's all the mesh vertices, so could be in the millions even. But let's try to find a meaningful reduced model where we replace X by this formulation f of t, and t is the parameters of the reduced model. So it's living in some m-dimensional space where m is much, much smaller than n, because we know that most deformations are not going to be meaningful. So the meaningful ones are all the vertices of the mesh are somehow correlated, obviously. So the question is how to design this f of t, of course. What is t and what is f, right? And if we manage to do it, then we have a much smaller optimization problem to solve here, only in m parameters. So what Alec proposed was to use a very well-known subspace formulation from the gaming community at the time, and that's called linear blend skinning, or skinning in general. It's a very simple deformation technique where you can have skeletons or handles or even cages around your shape. And the prescribed transformation at those handles, for example, bones of a skeleton, are somehow smeared over the whole object using the so-called linear blend skinning technique. So how does it work? First, someone, the user or an algorithm, places these handles on the shape. Then there are weights computed, or normally in the industry, they're just painted by hand. You have these weights for each handle. These are numbers between 0 and 1 over the entire surface of the shape that say how much that handle affects each point on the surface of the shape. And then in real time, to deform the shape, we provide transformation matrices, so rotations, translations, scaling, things like that, to each handle. And these transformations are just linearly blended over the entire surface using the skinning weights, these W's that we saw earlier. So you see, this is a super, super simple formula. And the nice thing is that you can compute the weights and then you upload them once onto the GPU, and each frame you just need to send to the hardware these transformations T, which is a very small amount of data, and the linear blending is happening in parallel for each mesh vertex on the GPU. So it's extremely fast. It's what we call ridiculously parallel, right? So it's a super efficient technique. You might ask, why not use it all the time? Why all this complication with, energy optimization? There are two problems. Problem number one is we have manual weight painting, and it's a very tedious and unintuitive process for artists or just for general users. So what we contributed was an algorithm to compute these weights automatically. And the other problem, it's maybe even more severe, I would say, and that's these artifacts that happen due to this linear formula. Sorry, somehow my video is not playing, but here you might see that in the elbow, there is this problem of it becoming very flat. And that's because when we're blending rotations that are very far away, so let's say 90 degrees and minus 90 degrees, if we're doing it linearly, we're getting 0, right? We're getting a collapsed singular matrix. And the same thing might happen with twisting transformations, as you see in the right video here. So we somehow need to solve these artifacts called elbow collapse and candy wrapper in the industry jargon. And here the idea is indeed to use this smart energy optimization that we had before that produces the correct rotations and everything to get rid of these artifacts. So I'm not going to go into the details of this, but I just want to kind of say that Alec Jacobson invented a magic formula to compute the skinning weights automatically. It's optimizing squared Laplacian of the weights over the entire surface, producing a very smooth function. And by adding these inequality constraints that the weights have to be between 0 and 1, we get non-negative weights that are indeed valid for this problem. And you can solve it in a discrete way by solving a quadratic programming optimization. So it's fairly efficient. So this is for automatic weights. They're called bounded biharmonic weights. You might have seen this somewhere already. It's a pretty established technique by now. And now that we have these weights, so how do we use the skin in subspace? So we get the handles from the user and also some ghost handles that I will talk about a little bit later. And then we have this following reduced model, right? So our deformed positions are expressed in this skinning subspace. And we can write it in matrix form like this. And a T is very low dimensional. That's basically the main idea here. And so when we optimize the air up energy, or indeed any energy, we have a very small number of unknowns here. So when we look at the formulation in a little bit more detail, so this was the air up energy from before. Now we are reducing it to the skinning formula, right? Which is, again, can be computed very fast and in parallel on the GPU. So now let's see how the substitution works. So basically, now instead of x, we have t as unknowns, and we have a very, very small problem to solve in the global step here. The only problem is the local step, because the 3x3 SVDs still stay very numerous, right? We still have a lot of mesh vertices that we have to solve the SVDs on, so it's quite slow. But here again, we can squeeze a bit more out of this formulation, because this subspace that we created based on user handles also provides us a very intuitive and meaningful segmentation or clustering on the shape. So we basically can cluster the mesh vertices based on the skinning weights, because if two vertices have similar skinning weights, they will deform in a similar manner. So we can do this clustering and only perform the rotation optimization per cluster. So that works much better, much faster, sorry. Obviously, you can see here a comparison on the dependence based on the cluster number. And in addition to enrich the skinning subspace, we also add some ghost handles. These are basically some random points that we sprinkle on the shape that are not controlled by the user, but they're there to generate a little bit richer deformation space and then enable more rotation or bending happening. So here I want to show you how it works. So this would be just a linear blend skinning. You see it's very squishy. It's it's not elastic, right? That's due to this linearization problem. And here is the result of the fast automatic skinning transformation approach, where you see that it really does deform elastically as it should. Here are some more examples on various canonical shapes, comparing to, sorry, maybe let me go back for a second. So the method on the left is an offline method that simulates elasticity. And here's this cactus that I showed earlier, but now not in 500 points resolution, but in full resolution, and the same for the bar. So it's a very flexible approach to deform and animate characters. You can do all kinds of fun stuff with it. Here's again the same octopus that you saw earlier from Laplacian editing, but now the deformation look much better. They're very, indeed, you have nonlinear elasticity here, and this is in real time with 300,000 triangles on this mesh. And the kind of crowning achievement of that work was to be able to animate independently 100 armadillo monsters. So we call it monster morning gymnastics. Here, because of the GPU parallelization, we can individually animate each one, all of them in parallel in real time. And this approach also works in 2D. So if you ever need to edit your photographs, you can do it like this. Here's the making the Mona Lisa a little bit happier. So you see, this is I don't know if we were allowed to do that to the Mona Lisa, so I quickly skipped that slide. If you want to try the software, it's all publicly available in libIGL, but also it's implemented in Blender, in Seagull, in Adobe products. In particular, Adobe Animator uses this framework. And we also have a student of mine did an iPhone app a while ago. So, okay, so basically I've shown you what happened in the early 2000s till, let's say, mid 2010, 2013, something like that. So the question is, okay, is the deformation problem solved? What are we even doing here? And what I say is that, yes, it's solved for rubber toys. I think it is, but not all objects are made of rubber. And maybe more prominently, the problem is solved if the user is willing to invest all this effort into defining the deformation space somehow, the shape space, by placing all those handles and controls and explicitly controlling them and saying, you know, for each skeletal bone, how it should rotate and so on. Or for each point handle where it should go. So it requires a lot of work and expertise from the user somehow. And moreover, we know that not all shapes are made of rubber, right? There are all kinds of different shape types that are all deforming in their own idiosyncratic ways, right? We have human bodies, we have human faces, hands, articulated characters that are not humans, plants, garments, you know, the list is endless. And I would like for the remaining of the talk, in the little time I have, I want to focus on human-made objects, which is a pretty broad class of these CAD-like shapes that I think it's interesting to think about, because those are definitely not made of rubber and still quite important to be, you know, to model, because that's the type of shapes that surround us. I think they're also quite important for computer vision algorithms to understand, you know, the world around us. And also that's objects that we use and are surrounded by in daily life. So what are these CAD or human-made shapes? Basically, you could say that for, you know, various reasons of design and functionality, these shapes are mostly smooth. So they don't have such fancy details as we saw before. They have quite sharp and clean features, maybe feature curves, something like that. And they have certain functionality, and sometimes, usually the form follows the functionality. So again, you might think, okay, this is now she's coming finally to deep learning. No, I'm not. So news, we thought about these problems also before the deep learning boom. And I want to highlight this paper from 2009. So I'm sorry, it's super old. My students raise eyebrows on me when I mention something from 2017, you know, but I have to talk about this work because I think it's super interesting and in some sense not yet really beaten even by the new approaches. So I want to highlight it somehow. Basically, in this iWires project, what we did is try indeed to create a shape editing method, just like what I showed you before, but not rubbery, something that tries to preserve higher level details, indeed these feature curves on an object. So basically the approach is we first take this CAD-like object and extract its feature curves. We analyze these curves and decide which class they belong to, such as circles, ellipses, quadratic curves. Are they planar, you know, or non-planar, and so on. We also look at the relationships between different features, such as symmetry, coplanarity, parallelism, and so on. And then when the user prompts some editing action, we first rearrange the features and then deform the surface in between using some very simple thing like ARAP or indeed even naive Laplacian editing would work, because the in-between surfaces are just smooth, nothing interesting is happening there. So maybe to show you a little bit how it works behind the scenes, so let's do this very simple example, a Lego brick. So here are the curves that the algorithm extracted and analyzed. And let's say the user is fixing this bottom side of the Lego brick and is pulling on the top side to go up like this. So at first, the algorithm just does an elastic curve deformation on this one, but then it fits back the class of the curve that it belonged to in the analysis stage. So in this case, it's a rectangle, so it fits a best fitting rectangle here. And then it propagates this edit to other curves. So for example, because this side was parallel and centric with respect to the right side of the Lego brick, we move it upwards so that it remains concentric. And then things are connected back. The deformation is propagated to the circles on these circular buttons on the Lego bricks. And again, we restore their class, so being circles. And the symmetry relationship. And in the end, the surface is deformed again. I mean, here nothing interesting is happening, it just stays basically you have planes and these cylinders here. And here's another small example. So this is a telephone dial. Again, this is like the old iPhone for the young people here. Let's say, so these are the curves that we extract. They're all circles and they have symmetry relation. So if the user is moving one of the dials in this direction, then first of all, the other ones are also moved because of the symmetry relationship. And then we restore the other circles and we edit elastically the remaining curves and restore their class to being circles. And finally, this is the surface. So I think it's quite amazing that it's possible to achieve such complicated edits as you see in the video in real time using this very rudimentary approach. And I think the smart thing here was indeed these rules that we encoded into defining feature curves and their class, so circle, straight line, square, and so on, and the relationships between the curves that we also hand designed in this case. Yeah, the things that were parallel should stay parallel, things that were perpendicular should stay perpendicular, and so on. So this was a lot of work just to define all these rules and relationships between features, and it's all made by hand. So of course, the question is how to automatically learn this from data instead. That's indeed the power of machine learning and data-driven methods, is to be able to learn these priors just by looking at enough data. And this is what we have been trying to do more recently, indeed, to instead of hand designing all these rules for what CAD shapes look like, let's learn a higher level shape representation and the relationships between shape parts using data. So in a recent work with Dani Kohenor, Amir Hertz, Or Perel, and Raja Jirius, we designed this spaghetti system. Don't ask me how the acronym, I don't think the acronym is related to the title of the paper, but you have to have an acronym in deep learning papers. So we called our network spaghetti. Basically, what we do here is we take a shape collection. So for example, chairs or airplanes or lamps, and the network learns a Gaussian mixture model and a neural implicit function that sits on top of these Gaussians and describes the surface of the object. And the nice thing is that when you have enough data of a similar class, then all these Gaussians are aligned to corresponding features automatically using this learning system. And it also models the interrelationships between the different Gaussians. So yeah, so we designed this architecture. I won't go into the details here, but basically it trains on ShapeNet, on a particular class of ShapeNet, and on those models, I mean, and it's able to reveal this representation, and then you can do edits of your shapes very similarly to what you saw before in iWires. Only now the relationships are not hand designed; they're learned automatically from data. So you can design, different legs for your chairs, different seats. You can move things around, and features are rearranged according to how, to whatever relationships that were extracted between different shape parts in the network. Here's another example of creating new shapes by mixing and matching parts from different shapes and also editing those parts. So you can see in the bottom the user action, and in the main blue part you see the result that is then generated by this spaghetti network. So you see that, yeah, it can produce fairly intuitive edits of the shape. So I guess, when we did that work, at first we had this euphoria moment of like, okay, we solved the problem. It's like iWires, but it's, everything is automatic, so problem solved. and indeed, the fact that you can extract these rules of editing CAD shapes from data is pretty amazing. But there are, of course, also downsides or things that are not yet solved. First of all, the learning is class-based. So if we try to run spaghetti on on all the classes of ShapeNet together, or even just on several classes, it works way less well. It gets confused. It doesn't know how to match these Gaussian mixture models across classes. It's by far not as good. There are also some still hard-coded things like the number of the Gaussians. So it's not free extraction of features like we had in iWires. And that's quite unsatisfying. The other thing is that it wasn't solved in iWires, it's still not solved today, is indeed how do you even ensure that the chair stays a chair? How do you preserve the object functionality or even just validity? I mean, functionality is very hard, but validity, ensuring that you don't get Möbius rings and Escher style objects, that can really exist in physical environment. It's still a very unsolved problem. And then, of course, these days, everything is about generative AI, diffusion models, and so on. And these are indeed super powerful, great tools, but you can't really, it's very difficult to control them if you want to get a specific result. They're amazing in generating creative, inspiring things, but when you really need something with, certain dimensions and certain let's say you have a concrete idea in mind, it's quite hard to force these methods to indeed produce it. So I think these are the challenges that we have, and maybe if I can steal 2 more minutes, I just want to kind of talk about this point a little bit more, this art direction and control by the user, or again, by an algorithm. That's a topic that's quite important, and yes, text-based generation is great, but sometimes it's just it's not the right tool for any concrete situation. So for instance, sketch-based shape modeling is a very popular technique because it borrows from our ability to draw in 2D and enables us to create 3D content, which is much harder than 2D. And sketch-based modeling existed, again, very long time ago. This is an algorithm from 2005, where Laplacian mesh editing is used together with sketching. So simply the positional constraints are provided via sketches in 2D. Here's another system from 2007 called fiber mesh, where we create shapes from scratch by drawing curves in 2D and then inflating an object that matches them. And it's a 3-dimensional object whose silhouettes then match the curves. And you can continue drawing these curves and deform them, and the object attains its shape this way. So here again, no deep learning, it's just, there is just a formula of curvature optimization that produces these 3D surfaces. And more recently, in 2020, together with some colleagues from Google Research, we expanded it to single view modeling and animation of shapes. Again, no deep learning. This is just a specialized ARAP version that works with single view drawing, and by layering constraints, we're able to keep a valid non-intersecting shape here, and you can even animate it. You're very welcome to try, by the way. It's a fully web-based application, Monster Mash. It's very fun to play with. Right, but of course, single view sketching is a classic thing that we could throw deep learning on, right? We could, because it's so ambiguous, right? When you just have a single view, how do you know what the shape looks like in 3D from other viewpoints? So it's very nice to utilize this priors that we learned from data, right? So what we did is we took the spaghetti framework and combined it with sketching inputs. And it doesn't have to be a very precise sketch. It can be quite, abstract. And based on the sketch, we learned this, again, this Gaussian mixture model that produces a shape from a certain class. So you see some results here. And here's a short video of how it might work. So in my lab, a lot of us have very poor sketching skills, and hence all these attempts to do research on how to improve on them, and despite no good artistic skills, produce something reasonable. Right, so I want to wrap up here, actually. I guess my point was, despite, the recent trends, I want to say that we did learn a lot in the past 20 years of geometric modeling and interactive shape modeling as well. But of course, we do need to learn some more. So all these classic approaches, they have their place, but there are many interesting challenges that I think are only solvable with, indeed, with machine learning approaches, where we cannot just model things using pure mathematics and geometry. We do need these data-based priors. And I think one of the challenges is how to deal with general versus specialized models. So currently we only have specialized models, indeed very specialized, only chairs, only airplanes, only lamps. And it would be great to somehow leave that restriction and have these ML-based models generalized better. And so that's really the question, how to benefit from deep learning superpower, but not be so restricted to the kind of data you're training on. And maybe one way is to indeed combine classic methods and learning methods via, geometry laws and physics laws, because those are universally true in our world, and they would enable generalization. I think if we somehow are able to teach the AI systems how to understand those laws, but how to do it, it's an open question still, I think, largely. All right, so with that, I would like to thank all my co-authors of the works that I've shown you, and all of the wonderful mentors I had over the years, and my students and postdocs. This is the current group that I have. Thank all of them for the amazing work. And I want to acknowledge the funding agencies. And thank you so much to the organizers for inviting me, and thank all of you for your attention. Thank you.